IRIS, which stands for Invisible Realistic Image Stressors, is a paper about a surprisingly practical kind of attack on computer vision. Physical-looking distortions that humans often do not notice that the cameras and neural networks react to strongly. The authors point out that modern imaging systems increasingly use cues outside ordinary human perception. Things like near-infrared reflections, timing effects from sensors, scattering, and other hardware-dependent signals. That gap between what humans see and what sensors capture creates a new risk surface. An attacker can introduce changes that look harmless to people, but still push a vision model into the wrong decision. Instead of focusing on the typical digital adversarial examples that require gradients, optimization, or training against a specific model, this work highlights a more overlooked class: closed-form, model-agnostic perturbations that are easy to implement and resemble real artifacts such as rolling shutter effects, aliasing patterns, spectral sensitivity mismatches, and flare. The paper's benchmark evaluates 20 such perturbations across 9 public vision datasets using standard off-the-shelf classifiers, totaling about 1.5 million model inferences. And the key headline is that simple signal processing operators can induce extremely high misclassification rates, sometimes up to about 96%, without any model-specific tailoring. Just as importantly, they don't hand-wave about whether the attacks are invisible. They quantify visibility using a standard perceptual color difference measure called delta A76 and del. They emphasize a responsible framing where robustness must be discussed together with human perceptibility, because works well is not meaningful if the perturbation is obvious to people. The benchmark itself is built as a library of lightweight, parameterized transformations applied to images in a physically plausible way meant to mirror distortions that could arise from displays, sensors, optics, and illumination. The operators cover a range of mechanisms: spectral tricks like adding near-infrared style patterns, temporal tricks like LED-style flicker banding and rolling readout ramps, spatial distortions like channel misregistration, moire fringes, and subpixel grid artifacts, and optical artifacts like flare and motion blur that match rolling shutter capture. Alongside the benchmark, the authors provide analytical reasoning about perceptual deviation, choosing parameters so that many perturbations stay near or below typical, barely noticeable thresholds while still stressing the model. In evaluation, they report clean accuracy versus accuracy under these stressors and relate that to perceptual distance. The results show a clear trade-off. Some attacks are extremely strong but also obviously visible. For example, a channel inversion type effect that dramatically changes colors, while others remain largely hard to spot yet still succeed at high rates, such as near-infrared dot patterns or rolling shutter-like motion blur. They even observe a strong overall correlation between how visible an attack is and how successful it is, but also highlight that the correlation is not absolute, meaning invisibility does not guarantee safety. The conclusion is a warning and a tool at the same time. Many real-world, non-optimized just physics and signal processing distortions can reliably break modern vision models by exploiting systemic assumptions like demosicing and aliasing, because some of these cues can come from everyday sources, like high-frequency lighting control or emissions from devices. The right defense mindset has to include sensor-level and pipeline-level choices, not only model-side adversarial training.